I'm recording now with everyone's approval of this meeting, so we can share with Eric. Okay, so the purpose of this meeting is to really convince Mike, the originator of this problem, and then to make sure what we're saying is correct. Okay, so first I want to make sure, Mike, I want to hear clearly from Mike that you're Hamiltonian. So I'm sharing my my screen here. Okay, let me share. I'm sharing. Okay, so I'm sharing my screen. Do you see my screen?
Mm-hmm.
Okay. So okay. So
Okay, then this K should be the same as the K, as Eric's K, right?
yes.
It
So
may be different from Anderson Yuval. I don't know.
Anderson Yuval, their Hamiltonian is 1/2 of this one.
Okay.
Okay, so we can go back to the previous meetings about this. I can show you Anderson Yuval's original paper. There was a factor of 1/2 outside of a bracket.
Mm-hmm.
Okay, so what confused
Just
me?
hang on a second. Hang on. Okay. All right. Yeah, this K and okay, you're right, because this will reproduce minus K times SISJ.
Yeah. Okay. Okay. So can you still see my screen?
Yep.
Okay.
Because no, I can't remember. I haven't gone through the calculations.
Okay. Oh, okay, Mike. Okay. So this Hamiltonian, when you write it down, is a sum of minus SI SJ over 1 minus J I minus J squared, right?
Yeah.
Okay. So in Anderson Yuval, there's a factor of 1/2 outside. Okay. So Bhattacharjee, remember the paper by Scalapino?
No, I don't.
Bhattacharjee.
Okay.
We talked about a lot about that paper. Their Hamiltonian has a factor of 1/2. So it's the same, their Hamiltonian is the same as Anderson Yuval. So their TC was 0.79.
All right. And so according to your measurements, I mean, your simulation, our TC is approximately correct, right?
It's twice.
What?
It's twice of their value.
Right. Okay.
Okay. So we're okay. So then what troubled me for a long time was how come your RG equation is the same as Anderson Yuval's? Okay.
I may well have slipped up with the factor of 2 somewhere because it.
Yeah, you did. Okay. So let me show you. So now I can show you step by step where you did. Okay. Okay, so this is your lecture 1. Let me zoom in Okay, zoom out, okay. Okay, so this is your lecture one, okay, Mike?
Yep.
Okay. So you're, okay,
So
so.
hang on. I've got to get all the things right. So
Mikey, this part is not important. The important
Right.
part is this start from here. The first mistake is here. I don't know what's Chaucher's mistake or my mistake. We define a spin as plus minus half. Okay, so this is the start.
I define the spin as, I think, plus or minus one.
Okay, so if you define plus minus one, okay, so then what's going to happen is I can tell you the okay, so I can tell you step by step where the errors were made. One was counting this when we apply the Euler-Maclaurin formula. Okay, so this one minus one is two. 2 squared should give me a 4. Okay. And then sum over 2n.
Okay, okay, that's just the nearest neighbor interaction.
Yes.
Right. But I mean, all that does is it changes the value of the fugacity. That's all.
Yeah. What I'm saying is in that formula, there's a factor of 8 here. When you do correctly, there's a factor of 8 here. Okay. And then I'm not forcing you to accept my algebra now. I'm just saying, if you just follow my discussion, you will see I can get the correct Hamiltonian mean at the end. Okay.
Okay.
Okay. So then when we do the second integration by part, when we get the Euler Mascheroni constant here, okay, so this charge here Q is actually not plus minus 1, it's plus minus 2. Okay, and then the difference across the wall is actually a factor 2. So there's a 2n.
Yeah, that's true.
Okay, so there's another factor of 8 here. Okay, so you will see this will come out to be correct. Okay. And then you see this s squared here is also 8. Okay, so I can show you where the charge has to be a factor of 2. Okay, because when we do the sum of the spin here, remember, in order to make it, so now I think I understand why Chaucher made it a spin to be half, because you told her the charge of the domain was plus minus 1. In order to make it plus minus 1, then the spin has to be half. But if you define the spins as plus minus 1, and then the charge is actually 2.
No, wait a minute. Then, wait a minute. If the energy of a domain wall energy, that's right, SI minus SJ squared. The SI minus SI plus 1 all squared. So that if those two spins differ by 1,
yes,
then that means you're talking about. Wait a minute. Yeah, okay. Yeah, you're right. Yeah.
okay, so once I walk you through, I will make a complete admission. I will tell you that ChatGPT helped me find out all your mistakes. ChatGPT find out all your algebraic errors here. Okay, Mike, at the end of the Hamiltonian is 2 k naught gamma and then times 2n here. Okay, and the q is plus minus 2. Okay, so then okay, so this is the end of the Hamiltonian. Okay, so then what does it mean for lecture 2? Okay, so lecture 2 is to derive the RG equation, right? Using the the tracing, okay? So when you do this procedure.
Okay, I know what happened at this point, because all I did was I just absorbed any free, factors of 2 floating around into the redefinition of the K.
Yeah. Okay. Okay. So Mike, you're playing loose with the factor 2 really caused lots of pain in us. Okay. So I'm
I'm
just
sure it did. I mean,
uh,
I wasn't worried about those sorts of factors of 2.
okay, okay, Mike. Okay.
The thing is,
I can tell you. Okay,
the
Mike, I can tell you.
point shown was that once I'd got the Hamiltonian into this domain wall form, whether the K I'd got written down had anything to do with the original K was a
Yeah.
bit irrelevant.
Yeah. Okay. Okay, Mike. I can show you exactly where the mistake was made. Okay. So when you do this sum here, when you do this rescaling, and then there's a factor here due to the rescaling. Okay. Now the Qi and the Qj, the factor of 2 makes a huge difference. Okay. Why?
Right.
Because then this is a 4. This is a 4. So when you take 2n out, it's 1 minus 2k. So
Right.
this is not a 1 minus k or 1 minus half, it's actually 1 minus 2k.
Okay. Yeah. Okay. I believe you.
Okay, Mike, this is correct. Okay. So then I can so just to be sure, okay. Okay, so what I did was okay, so your RG equation in your even in your review article you wrote it this way, there's a factor of 2 here.
Yeah, I can. Yeah, I believe you.
Okay. I'm okay. So what Eric did, his Hamiltonian is the same as yours.
Right.
Okay. So at the time he realized the RGA equation is 1 minus 2k, not a 1 minus k. So he just put a 2 there. Okay. But anyway, so to be super sure, to convince myself this is actually true, I asked ChatGPT to calculate for infinite ferromagnetic ground state to calculate 1 domain flip of X. So I created 2 domain walls. I asked it to calculate what's the energy. Okay.
Yep.
And then you see it's actually exactly 4 times 1 plus the Euler constant plus 4 times log X. This is actually really 4. The charge is 2 times 2. Okay.
All right. I guess you're right. Yes.
Okay, so then the rest is just algebra. Okay.
Right.
Okay, so then the question of km squared, that it needs to be a constant.
Yep.
Okay, so that straight comes out of the RG equation. Okay, so there's
Yes.
there's no question about that.
Right.
Okay. The question then is how do we interpret it? Okay, so how do we interpret? So this point here is little l equal to 0. Little l equals 0
sorry,
means
just a minute. I've got.
okay. So, oh, you probably cannot see my cursor. Can you see my cursor?
I've got a black thing that's got rid of it. Okay.
Do you guys know how to get rid of this black bar?
Okay, the scale of the K's you have here are right, yeah?
Oh, okay, hold on. Let me okay.
So the critical K is a half, yeah? It's
critical is a 1/2. Yes. Okay, let me get rid of this thing. Oh, okay, here it is. Okay. So yeah, it's 1/2.
Then the value of Km squared has to be it's a renormalization group invariant. And so that has to be a half at TC.
Yes.
Yep, not 1, right.
Right. Okay. So okay. So the question is the question is, how do we, okay, so let me first make sure I understand the RG concept correctly, that when km square goes from this point here,
Hang on,
and
hang on. I can't see. What do you mean by this point?
okay, let me see if I can draw. Okay. This point here.
No, I'm sorry. You're not showing me anything. I don't see
Okay,
it.
and then I'm trying to draw. I'm trying to draw. Here.
Oh,
This
okay.
that's L equal to 0, isn't it? L equal to 0 here, right?
So I'm confused.
This is L equal to infinity. This is the infinity.
I'm sorry. I'm sorry. I don't understand because km squared must be a constant on any of these renormalization group.
Right. So which
Check.
means km squared is the same at this point and at this point, right?
Any point along the line, it's the same.
Right. Okay. So that means you agreed this is L equal to 0. This is L equal to infinity, right?
I'm sorry. It's 1 equals 0.
The here, the beginning of the RG.
Okay. No, at the beginning of the RG,
There is a bare fugacity, right, Mike?
yeah, there's some bare fugacity and there's some initial value of k.
Yes.
Right.
Okay. So from that point on, then when you look at a system at the larger length scale, km squared is a constant.
Yeah.
Okay. So the m square we calculated using the RG theory is using the fact that the km square is equal to a constant.
If you like, yeah.
Okay. So then
you have to figure out
m
what that constant is now.
yeah, yes. So m square at the infinity is 1.
Yeah, when you normalize it, it's 1, right? So
Yes.
then the constant is just the value of k at infinity.
Yes. Yes. But
Yes.
the k, Mike, the k changes on the RG line.
I'm sorry?
K is changing as a function of length.
Yes.
Okay.
Yeah. I mean that is k it changes as a function of length scale.
Okay, so we have the same so we have the same understanding now. Okay, so that's
Yeah.
good. Okay, so that means I did not misunderstand you. Okay, okay, so okay, so okay, so then we now go to the data. Okay,
Mhm.
okay, so these are the facts. If you look at m squared versus t, for different length, there's a crossing for what you call the simple periodic boundary condition. Okay?
Okay.
And then this crossing is absent if you use this infinite sum periodic boundary condition.
I'm sorry. I got lost.
Okay, so we tried 3 different boundary conditions.
Mm-hmm.
Open boundary, it has a crossing. Simple periodic boundary condition, it has a crossing.
Right.
When we use the infinite number of images, the crossing goes away.
I can believe, well, yeah, okay, I can believe that anything can happen with different boundary conditions, but
Okay, so, and then when you compare to the peak of the susceptibility, the peak of the susceptibility happens above than the magnetization crossing.
okay.
So which means the peak, since the peak we interpreted is where the correlation length reaches the size of the system, right?
Think so.
Okay, so that means the crossing
Well, not
happens.
necessarily. So if you're far enough away from TC, the correlation length is probably always less than the system size.
Yes. Mike, here, at t equal to 2.5, clearly the correlation length is less than the system size, okay?
Mhm.
Okay, so when you reach something like a 1.7, and then for L equal to 400, the system size has been reached by the correlation length.
Probably, yeah.
Okay, below this temperature, okay, then the crossing happens. So this crossing happens in this finer size system in the ferromagnetic state. Do you agree to that statement?
Oh God. My mind is is operating a lot slower than yours.
Okay,
Hey,
we can slow that.
Sean, do you want to say the crossing occurs at the critical point at case
No,
at
no,
TC?
no, no, no,
You don't want to
no.
say that.
We
Okay.
don't want to say that.
Okay.
I want to say what I want to say is
surely this crossing only happens in a finite system.
in the infinite system, there is only one line, Mike. There is
Right.
no crossing to talk.
Yeah.
Yeah.
So I mean, the thing is that, I mean, I'm not exactly sure. I don't know how it happens in detail, but you know, as soon as you got a finite, so this crossing only happens in a finite system.
Yes.
Finite system, you need boundary conditions.
Yes. Exactly.
And so it all becomes very complicated. You know,
Yes.
you don't know whether what this crossing means.
Yes.
Okay, I mean, people do use this sort of crossing to sort of try to extrapolate, you know, to thermodynamic limit and stuff like that. But I don't really believe in these extrapolations.
Okay. Okay. Mike, before we get into the opinion, let's just go over the facts first.
No,
Okay.
no, for the very simple reason that I don't understand, you know, in detail what's going on. I mean, that's really all it is.
Okay, so let me let's go over the facts, and then then I like to hear your opinion. Okay.
I mean, to tell the truth, I don't think one should make too much noise about these crossing points because they are strictly a finite system effect.
Yes. Yes.
And
But
so,
it comes out of RG, Mike.
sorry?
comes out of the RG, the magnetization from the RG calculation gives us the crossing.
Well, I never followed that argument, possibly.
Okay.
I don't quite understand how the renormalization group predicts the crossing.
Okay, yeah, then let's, okay, so then maybe we should go there right now. Okay. So the first, okay, so this is the figure 4, okay?
Yeah,
You see the 3 solid lines, red, green, and black.
yeah,
They are the RG equation from straight out of your formulas. The black line is equal to little l equal to 0, so big L is equal to 1. So in other words, before the start of the RG flow. So black line is calculated using the bare fugacity.
okay.
Okay, so the green line is the big L equal to 1,000.
Yeah, but I mean, sorry, which bare fugacity? The bare fugacity in the pure 1/r² model, or what?
Yes, we'll only talk about pure model. Mike, I did not add any in your paper. You talk about adding the extra A term. We get rid of that.
Okay, so you didn't do that. All right, so
I didn't do that.
the fugacity comes out, whatever, as you say, whatever it comes out to be.
Yeah. Mike, the fugacity term, this 1 plus the Euler constant, came straight out of a discrete model to a continuum. So basically, it's, if you think about a 2D solid, it's like the Parrell's potential, essentially.
Yes, oh yeah.
Okay, so this is for this 1/r² Eisen model. There is a bare fugacity, and that's bare fugacity is just dependent on the 1 plus the Euler constant. Okay, nothing else.
The trouble with actually fugacity varies with temperature as well.
Yes, exactly. That's why the TC, when you combine the 2 equations, and then you will give you the bare fugacity of 0.133. And then the TC from that will be 1.563.
So Sean, in your
Yes.
equation in the paper,
Yes.
it's unclear what, so if in the paper, it's unclear what K0 of TC is. Because you write I0 equals minus K0 of TC times 1 plus gamma.
Okay, hold on.
Either than minus that.
Okay, hold on. I have it here. I have it here. Okay, so
you see this equation right there, equation 7?
yes, there's a factor of 2 here. Yes, you are right.
Oh, you're going to put in a factor of 2 there?
Yeah, I will put it there. Yes.
Oh, if you do that, then it'll work.
Yeah, I can tell you where that factor of 2 comes from. Okay, the factor of 2 comes from so if you correct Mike's typo here, put a spin here, okay, and then remember this is 8, right? But this is for spin, so there's a factor of half. He didn't include it here yet. Okay,
Right.
Once he included a factor of 2, this becomes 4n, and then remember is take out the 2n, right? So it's 2 gamma here. Okay, it's 2 gamma here, and then there's a 2 here. Okay. And then so when you put it together, is 2 times 1 plus gamma.
Okay. Well, I'm good with that if you put the 2 in there.
Yeah. It's,
Okay.
yeah. I just forgot. I haven't. Well, actually,
Okay.
I should have done it, but I forgot. Yeah.
Okay.
Yeah.
So
Yeah.
in
This.
equation 7, you will have -2 times
Yes.
K0.
Yes.
Okay.
Yes. There's a -2 there.
Okay, good.
Yeah. And then all the numbers come out to be
Then
consistent.
the numbers
Mike,
come out right, yeah.
yeah, Mike, I want you to be absolutely clear about this equation 12. Mike, are you here?
Yeah, I'm here.
This
Oh.
equation 12 is the infinite sum periodic boundary condition. It's not ours. We used what you call the simple periodic. What we used is this one. Is the Lee J introduced us to this, and it turns out to be the best.
The best for what?
Okay, so Mike. Okay,
Yeah, I like that. Good point,
okay,
Mike.
okay. Okay, Mike. Okay, so so this is Jij versus K. Okay.
Right.
Okay. So basically then this is the coupling constant. The red one here, it looks like brown here. Okay. The circle one,
That's the summed one, is it?
this is the simple one. That's what's called what Jane called a minimal image.
Periodic boundary condition.
Oh boy. Okay.
The blue one is the infinite sum.
This gets too complicated for me because I see at this point, these putting periodic images on drives me sort of insane because now hang on a second. Hang on. The original interaction is just 1 over. What's the bottom axis?
The distance.
That's I minus j. Okay. Yeah, but the original interactions is just 1 over I minus j squared.
Yes. That's what these lines are. Yeah.
Which line is that?
Is where they agree, where they overlap.
Okay, now, all right. Yeah, all right. So then the blue line is what?
Mike, I'm gonna draw a circle. Okay, so let's put a spin on it. Okay, so basically, when you count the distance, this guy, okay, once you reach to this side, and then that's the cutoff. That's half L. That's this point here. Okay.
Okay.
This brown curve is a hard cutoff. Okay. This blue one is the clever one by adding more image charges. In fact, add infinite number of them. This was first introduced by Bhattacharjee. And Eric just used theirs.
Okay.
Okay, so if you look at the difference between the two, that's the difference between the two. So there is a you effectively add a long range, infinite range interaction to the system, and then some more. So my belief is this infinite sum effectively adds a infinite range interaction. And then we know what an infinite range interaction would do to a model like this. You basically make the TC to be infinite.
Infinite range interaction.
No.
I mean, field. Field behavior.
Yeah, the system is ordered at any temperature.
I'm sorry, it's ordered.
The system is ordered at any temperature.
Yeah.
So basically, when you add a long range, this kind of interaction, I think it changes the physics completely. I know this statement sounds.
I'm not convinced of that. Didn't Eric do simulations with the infinite range, with the infinite periodic boundary? And he got a finite transition temperature.
Yeah, I mean, the thing is that if you have an infinite range interaction, you have to take the coupling constant, to zero in the right way, so that that you have that something is some combination of the number of spins in the chain and the coupling constant is finite to actually get a transition.
Okay. Okay. So
if you don't do that, like Sean says, it's ordered at ordered all the time.
okay. But Jane just pointed out something. I want to address that. Okay. Let me see.
Yeah, I mean, it's like saying, all right, I'm adding together an infinite number of things, and if I want something finite, I have to be very careful to make sure I get cancellations, or each piece is small enough so that the infinite sum is finite.
Yeah. So
one or the other.
yes. Okay. So
now what happens when you use these weird boundary conditions? Are you adding up a lot of small quantities, or are you adding up lots of things that cancel each other, or what exactly are you doing?
You just no, everything, because it's positive. Every number you add is positive.
Then if that's the case, then you're certainly going to change the physics. I mean, there's no question that an infinite range interaction is going to give you it's not going to give you a transition.
Okay, so to answer what Jan just said, wait a second, but didn't Eric see there is a final temperature transition? So I'd like Eric to answer for himself, okay? But I'm just copying his numbers here. So the KC here, the 0.6398 is from inverting the 1.563. Okay, I didn't do anything else fancy, just inverted.
Oh boy, okay.
Okay, so then this is Eric's. Okay, so this is a 0.6548, and so he has different way of analyzing data. He get these two different numbers. Okay, so I believe, this is my personal belief, so I'm going to share this video with Eric. My belief is using this infinite sum periodic boundary, and they use that data to do that RG analysis. So his RG analysis, I'm copying here. And then it's basically by expanding the M square formula we get from RG and then expand it as 1/L. You get this formula 4, except B1 would be negative. But at the time, he didn't realize this B1 can have a negative sign. And then he just assumed B1 was positive. And then, so I believe that transition temperature he got was just invalid. And then I will share the video with Eric, and I will let Eric to defend himself or criticize me himself. But this is my belief. Okay. Okay, so
But in his simulations, what did he use to determine the transition temperature?
oh, he used the he fit his magnetization with I have his paper here. Fit the magnetization with the
There it is. Where is it?
um
Let me
somewhere.
see if-
Um this one. Mm.
Yeah, it's a Fitzrev letters,
Yeah.
2001.
Yes, so the way he fitted was to fit his magnetization into a threshold of a as a function of k, and then he fitted into essentially a square root singularity there, and then try to get a TC that way.
All right.
Is that standard?
Sounds like cheating to me,
Yeah.
because there's something peculiar about these many, infinite number of image potentials. I don't like that at all. It's like trying to say, okay, what I'm going to do, I have all these Fourier components, and I'm going to add them together numerically. And when you do that, do you really expect to reproduce what you started with? I don't think so.
Uh,
I can go to my desktop real quick and resend the paper in an email thread if you can't find it.
yeah,
I have it if you want me to share it.
yeah, okay, okay, let me let you share, okay. Let me, oh, I need to stop sharing, okay.
Yeah, you have to let me share.
You're a co-host now, so you can share.
All right, so do that.
The trouble here
Okay.
is I don't want to,
Okay,
although you might think that some of these tricks that have been used are all a load of bullshit, you don't want to say so in this paper, because that'll lead us into trouble.
Okay, so Mike, I think this paper, to me, what's very important is to correct, number one, your mistake. Because
I'm sorry?
to correct your mistake. Because your factor of two really made us suffer quite a bit.
That's what comes of not checking the calculations. If you go to a numerical comparison, you check that the analytic stuff is right.
You know, when Jonah was writing his thesis, he came to my office almost crying because couldn't get the factor of two because it's a factor of two is a big number. You know, his curve and but the charge is they just do not agree. So anyways,
consistently out with the factor of two, obviously a cock up in the analytic work.
but because we didn't know where was the mistake, so that gave us lots of anxiety, right? Um,
So here's the point that I think I want to make. Do you see this figure 2?
yes,
So he's calculating this susceptibility as a function of K.
yeah, but he
Okay?
did not. Just want to make sure we understand that his susceptibility is m squared.
Right. Yeah.
Without subtracting the spontaneous magnetization.
Right.
Yeah.
Right. So
Once he
you're
did,
assuming-
he will get a peak. Yeah.
Yeah. So he gets, and he fits it to the, the essential singularity, this thing over
Yeah.
here,
Yes. Yes.
right? And
Yes.
so you do get, and this is using the infinite sum.
Wait a
Yes.
minute, it's impossible to fit data to that. I mean, okay, that the prediction of that essential singularity is probably right, but you can't pretend to fit data to that.
Yeah, yeah,
I mean,
but at least you
it's
get
ridiculous.
some idea of what KC is, don't you?
Yeah, I mean, it's the essential singularity is diverging so fast
Right.
that any data fitting is just a nonsense. And anyway, the range over which you get just that essential singularity is tiny. If you go a little bit away from outside that little range, you're going to get corrections, which are probably also divergent.
Yeah,
So you've got so many parameters to fit that the whole fitting becomes nonsensical.
yeah, I agree. I don't know how good the fit is, but the point is the susceptibility is clear, it seems to be diverging at at some finite K. So there does seem to be a transition. Isn't that what he's, even
Right.
with the
I mean-
infinite boundary conditions?
I mean, that's the best you can use this sort of data for.
Yeah,
There seems to be some transition. Okay.
that's all I'm saying.
Yeah, well, I think that's a valid point. Saying what Jane is saying, if we say the infinite sum gives us a infinite range interaction, the system will not have any divergence because the system is ordered at all temperature. Jane,
And I'm
is
not
that what you're
sure
saying?
that's true. I'm not sure that's true.
Unless you take the appropriate limit,
Mhm.
because if you take the limit of the interaction constant going to zero in the right way, then you can get a transition in the infinite range model.
Let me give you another example. You know, the two-dimensional, one component plasma, 1/r potential, right? Everybody agrees that in 2 dimensions, there's the usual, some kind of Kosterlitz-Tauss phase transition between a liquid and a solid, right? Everybody agrees to that. But because 1/r is a long-range potential, all right, if you integrate it, you're not going to get the correct limit unless you have these infinite series. You do this Ewald sum.
Right.
Everybody, I'm pretty sure everybody does the 1/r potential in 2D uses an Ewald sum, which is what this thing is equivalent to. This infinite sum periodic boundary condition. That's my understanding. So it's not clear to me why it would lead, why an infinite range potential always leads to, always in the ordered low temperature state.
Yeah, okay, but I think that I think what happens is that you have to be careful about how you know how you actually do the calculation.
Yeah, that's,
For
if you're
instance,
doing
like
math with it, I'm sure you're right. You have
in
to be
3
very
dimensions,
careful in 2
the total
dimensions.
potential.
Yeah,
You
right.
have to put in some, if you want to get any sense out of it, you have to put in some neutralizing background.
Yeah, that's right. That's right.
And so,
Right.
I mean, because when I'm talking about the infinite range potential, I don't have the equivalent of a neutralizing background. And so then, all hell breaks loose.
I see what you're saying. Let's see. So in the simulations, what they do is they use this Ewald potential, which gives you, instead of just 1 over R, you do some kind of infinite series, and you get some other formula for it. Just like in our paper,
Right.
you get this cosecant squared thing.
Right.
It's the same kind of thing. So this equation 12 is what they used for their how they would do the simulations. And it's,
So,
It was-
so, so,
This
so
is one
Jen,
strange interaction, but what is this? It's fine as long as I minus J over L is small. Okay, then it is like the 1 over R squared potential. But
right.
when I minus J is compatible with L, it's basically a long range potential, basically a constant independent of I and J.
Right. Well, I and J, let's see,
I mean, there's a big range of I minus J,
right,
where I minus J over L is finite.
is in the Jen, is in the second to the last figure of the supplementary material.
Yeah. And then you see you in that range of I minus J, you have basically a potential as a constant.
yeah. So
It's only when I minus J over L is very small that it goes to the 1 over I minus J squared.
yeah, no, I agree with that. That's certainly true. Yeah.
And so I'm not sure, I don't,
I think the issue is if, let's say, imagine a real system that's infinite,
it's very strange.
all right? A real infinite system,
Yeah, and I've
right?
got
And you want to model that with something, with some finite system. Well, as you go further and further out, if you integrate out everything, you'll, like you said, you'll get some infinite thing. But as you look at the effect of I minus J is that there is a strong effect because the potential is not falling off fast enough.
exactly, yeah. I mean,
Right.
the thing is that
That's
if
right.
I minus J over L is just finite,
Right.
a half or something like that, or a quarter,
Right.
or a third, or an eighth or something, then basically you're talking a constant potential.
Yeah.
What Jane is
Well,
asking,
anyway,
I think Jane, your point is still not addressed here. I don't hear a consensus here. That is, if there is effectively an infinite range interaction been added, how come there's still apparently a divergence stability at a critical temperature in Eric's simulation?
Right.
So one possibility is the infinite range term added is several orders of magnitude smaller. Yes, the system is ordered, but the corresponding spontaneous magnetization is actually small
Yes.
in magnitude.
The thing is that this cosec squared actually is small when I minus j over L is non-zero. It's only when I minus j over L is very, very small that this looks like a 1 over r squared interaction. See, otherwise it looks just like a pi squared over L squared interaction.
Yeah. So an L is big, it's small.
And that's a constant, and so because L is never infinite.
Right. So
Yeah.
if you have a constant potential, that doesn't do anything, right?
Yeah.
No. If the total energy is a constant, no, it's remember this is the coupling constant.
Exactly. Yeah.
It changes the order.
Yeah, but that's the point, is that this this form of the interaction is, to me, very unrealistic. It's fine as long as I minus j over L is extremely small.
Hmm.
Because then you do get the 1 over I minus j squared interaction. Yeah, because it's 1 over sine squared, so it's approximately 1 over the argument squared, and that cancels out the L squared, and you get 1 over I minus j squared.
Right, yeah.
It's
that's
only
right.
true for I minus j much smaller than pi over L.
Okay,
L over pi, I should say, right? It's where the argument is very small.
yeah,
That's a good representation of a 1 over r squared interaction. In the thermodynamic limit, it's
yeah,
fine, because then
yeah,
I minus j over L is very small.
yeah.
Okay. So then
Yeah,
I think
I think that's the point, yeah.
okay. So
Yeah.
I think I'm ready to. So it's our time is up. I think I'm gonna accept Eric's argument that his 2001 PRL is not a mistake. As I originally said, I'm gonna say so we will characterize it as the result he got was a result of the boundary condition he used. However, if we use this simpler hard cutoff, then we do see recover the crossing we expect from the RG. Okay, so I want to make sure
That statement I think is fine.
okay.
Yeah, what you just said.
Sean,
Yes.
about this crossing thing,
Yes.
I'm going to be very careful, because the RG is really only correct in the thermodynamic limit. So otherwise, you talk about finite size corrections, and we're not really within the RG. We're not doing that.
Okay, so let me make sure I understand the so this equation here, this plot here. You see my screen?
Yeah, yeah, I
Okay.
stopped sharing.
No, okay. Okay, so so in terms of where the crossing comes from, okay, so the dashed line is KC. Okay. On the left hand side is above TC, on the right hand side is below TC. Michael, are you with me on there?
Sorry, I don't understand really what you're saying, because remember, you're talking about a finite system.
Mike, I'm just trying to make sure we're on the same page in terms of the discussion, okay? So what I'm saying is at 0.64 is the critical KC, critical coupling constant. On the left-hand side is above the transition, on the right-hand side is below the transition.
No, okay.
On the right is ordered, on the left is disordered. Do you agree?
Okay, yeah, and thermodynamic limit, yes.
Okay, in thermodynamic limit, the M goes to 0 at TC. So on the left-hand side, TC is always 0 in the thermodynamic limit. Okay? Mike, so you are right, there is no crossing in that limit. Because,
Okay.
because the magnetization at all length scale vanishes at TC.
Right.
Okay. We agree on that. I understand what you're saying. I hope you understand. I understand that. I hope you, I know, Mike, you still view me as an experimentalist, try to do theory. You find it scary. But the experimentalist has a habit of trying to fix in the holes, okay?
Yeah, okay, yeah, right.
Okay, so you have to give the experimentalist credit that we can find the holes and then we can fix it. Okay,
Okay.
okay, so now at a finite size, okay, then M squared is not 0 anywhere. Do we agree on that?
Okay.
Okay. On the left-hand side, in the normal state, in the paramagnetic state, then is controlled by central limit theorem. Then combined with finite correlation length, that will give you a M squared goes as the correlation length over the length of the system. Okay, the algebra is extremely simple, even an experimentalist can work out.
Yeah, there's the standards of scaling argument, right?
Yes, yeah, okay. And then on the left-hand side, then the larger the size of the system, the smaller M squared. Do you agree?
I'm sorry, can you say that again?
Larger the system size L, the smaller the M squared, because it goes as 1 over L.
Wait a minute. You
The
have to
larger
compare
the
the
system,
correlation length of the system size.
yeah, the correlation length over the system size, yes.
Right.
So for larger L, M squared is smaller.
Above TC.
Above TC. So the magnetization should look like this. Okay, so
So you have to be careful here, because you're saying that something is proportional to the ratio of the correlation length over the system size.
yes.
Okay. So then,
Okay, like this.
in the thermodynamic limit, that quantity has to be 0.
Yes.
Right. But the magnetization is not 0 in the thermodynamic limit.
Yes.
So
No.
it can't be like the correlation length of the system size. unless you're below TC, when you can argue the correlation length is the system size.
Yeah, yeah. Mike, I think we agree on that. Okay, so what I want to say is, this is what you, okay, so.
And also, Sean, you have to be careful because you're writing this paper for, you're going into the expert, the phase transition experts territory.
Yes,
And so you have to be careful what you say.
yeah. Okay, so you already caught all my mistakes in terms of my experimentalist approach to make claims in theory. Okay, I accept that. Okay, so I'm gonna accept your suggestions. Okay, I'm gonna accept that.
One of the things is that.
Okay, so Mike, Mike, I want you to understand what I'm saying here. Do you see what I draw the green curve here?
I'm sorry?
Do you see I draw a green curve here in the paramagnetic state?
No, wait a minute. There's all sorts of things you've drawn in. Which one are you talking about?
I only draw two lines here. On the left-hand side, one is red, one is green. Oh, shoot, I forgot your color
Red, green,
blind.
fine.
I can sort of see the reddish thing versus the greenish thing. Okay.
Okay, okay. The reddish thing is a bigger L. The greenish thing is a little L, smaller L. Do you agree?
I'm sorry, I misunderstood.
The green one corresponds to a smaller system size. The red one corresponds to a larger system size. So the two lines I'm drawing is what you expect from central limit theorem.
I mean, basically, smaller system size, the curve is less.
For a small
all.
system size, you'd expect the magnetization to simply,
Bigger.
well, yeah, but I mean, at small k, it would simply tail off. Tail off to.
Yes, yeah.
But for larger systems, you expect it to be sort of follow the theoretical discontinuity for a while and then tail off.
Yes.
Yeah.
So this is why from the RG for finite size system, a crossing is expected.
And I never understood why the renormalization group argument gives you the crossing. I must confess.
Okay, so Mike, do you see the three curves on the right of the solid lines, the red and the green? Okay, let's just focus on the red and green.
Yeah.
Okay, the green one is L equal to 1,000, and the red is L equal to 1,000,000. That's from your formula. I'm just calculating M squared using your formula.
Oh, guys, I gotta jump. Yeah.
Okay.
I thought, yeah.
Okay. Mike, what you were saying is this. The reason the magnetization at a larger system size below TC, this is below TC, the magnetization is bigger, is sort of looking at a American political map. If you look like Texas, it's all red. If you look at a larger land scale, okay, it's all red. The whole state of Texas is red. But if you zoom in, you will see different patches of blue.
Sure.
Okay, so the magnetization is smaller when you look at a smaller length scale. When you look at a larger length scale, And then because of the broken symmetry, the system looks all red.
No, hang on a second, hang on. If you look at a small length scale, you'll see the magnetization.
Fluctuations. You
or-
see fluctuations.
or small.
Yes. Yes.
And some there's negative. So the point is that, over the whole system, and over a long time, it's got to average to zero.
No. That's above the transition. Below, we're talking about below the transition. Below the transition, the system
Is
has
not in a finite system that is no transition. So you have to be, you have to be careful here.
Mike, I'm trying to.
Because, when you talk about the magnetization, what do you mean by the magnetization? Magnetization really means an infinite time average.
Yes.
And that has to be zero in a finite system. I mean, there's a rigorous theorem that says that.
Yes, Mike, but in RG, we are not making a system.
RG is for the infinite system.
Yes.
It's not a finite system.
Yes, in RG, this RGL dependent magnetization is a magnetization you look at the different length scale for infinite system. Yes, the system is infinite, but when you look at the magnetization at a different length scale, you count the number of spins per unit area. That's the quantity you are measuring. The system has spontaneous magnetization, so this M is never going to be zero because it has spontaneous magnetization. But when you look at in a smaller system, you see more fluctuation, so magnetization gets smaller. And then when you zoom out, the magnetization gets bigger because, as you said, the system has broken symmetry, the time average, the magnetization looks bigger. This is your RG says that.
Okay.
Your material, and then just
what actually happens in a genuine very long time simulation of a magnetic system, as a function of time, the magnet, you start off the spins all up, right? Then as a function of time, the magnetization is going to decrease, and it's going to end up roughly at this positive equilibrium magnetization. Stays there for a while, and then basically,
Mike, no one disagrees, no one argues about that.
Time stays at minus m naught for some time, then it flips to plus m naught, stays there for a long time, and so on and so forth. But the average magnetization is zero.
Yes, Michael, we agree with that. That's not what we're talking about here. I'm talking about the three solid line from RG. RG, this magnetization is a length scale dependent magnetization for an infinite system.
So, Mike, isn't it in all these calculations, aren't you really looking at when you're looking at the thermodynamic limit, you're thinking of the situation where H is close to zero, but not equal to zero. So you first calculate the magnetization for H not equal to zero, then you take the limit as H goes to zero. So that gives you a finite magnetization, not zero magnetization. Isn't that what you're really doing?
No, what I was talking about was I was doing a simulation in strictly zero field.
Oh, then if you do it, you wait an infinite time, you will get zero because eventually
that's what I'm saying.
Yeah, that's true. But that's true of anything. That's true of the 2D icing model.
Yes.
Nearest neighbor, you get zero.
Like no one argues
unless you put on boundary conditions where the spins are all up, at the boundary, the spins are up.
Right, yeah, you could do
then
that.
you get a,
But that's like having a small magnetic field on or something like that.
yeah,
And letting that field go to zero.
right.
Mike
I
and
do
Jen,
agree. I do
both of
agree
my
with you.
students understand spontaneous magnetization. Why take it thermodynamic limit and the field to zero, the two limits in the right order? They understand that. We understand this. We're not arguing about that.
That's
Mike,
what I'm trying to say. We're not.
Okay.
Yeah.
Okay, so Mikey, you need to give some faith to your experimentalist colleagues, okay?
Oh, yeah,
Mike, okay, Mike,
yeah.
I'm telling you what you told me years ago, okay? Okay, that is in RG, you look at the magnetization at a different of an infinite system at different length scale, okay? So as you look at the system at a bigger and bigger, so this is after we already did the correct thermodynamic limit and then take the field to zero. So we already did the spontaneous magnetization proper procedure. Okay, we already did that. Now we just look at the system at a different length scale. We look at the magnetization. So this three curves. Let's just look at two curves: the red and green. Okay. The red is for L equal to 1,000,000, green is for L equal to 1,000. Calculated using the RG formula.
Yeah.
Okay. So what I'm saying is the RG formula gives you a magnetization crossing if you want to make the connection that your RG magnetization at the finite length scale for an infinite system is related to the Monte Carlo simulation of a finite size system. Okay, so no one ever proved the two are equal or how they're related. But what I'm saying is if you compare these two things, one is the RG magnetization crossing, and then the Monte Carlo simulation magnetization crossing, the two are strikingly close, and then there is a strong similarity in there. I think that statement we can make in the paper.
I mean, if you want to take your argument to the extreme, you take a very small sample, of a single spin or two or three spins, and of course the magnetization is +1 or -1 in that little domain because all the spins are all pointing up or down.
No, Mike, if it's in the infinite system size, if you look at a small, even you look at a unit cell, the magnetization is not zero because the system has broken symmetry. Remember, it has spontaneous magnetization.
Forget about this broken symmetry and stuff. If you just take a little piece of your system,
Mike, no one argues about that. Mike, that's not where we're. That's not where.
Well, going to be parallel to each other. It's only when you get to much larger blobs that you see that the magnetization of the blob is close to the equilibrium value.
Okay. Okay. So.
Of course. That's
okay.
In a very small blob, it's going to be +1 or -1.
Okay. So, Mike, I think I got everything I could possibly get out of you at this point.
Oh, boy. That's probably true.
Okay, so
That's
I think
probably a true statement.
okay, so I think this is a good conclusion. I know exactly, Mike, what you are saying. I know you're worried that having an experimentalist to write a theory paper and then make a strong statement make you worried. I will accept Eric's comment about characterization of his 2001 PRL as a mistake. I will not characterize as a mistake. I will just state as a matter of factly what that paper is about, and then the findings of our paper, and then we correct your factor of 2 in the RG, and then
Which 2001 paper? I'm sorry.
the paper
The one that Eric wrote.
Jane just shared.
I'm sorry, what?
The one that Eric wrote and that I shared on the screen, that was in 2000.
Okay. All right.
Yeah.
If you want to say rude things about a paper, if the paper's yours, that's fine. If it's somebody else's, you're
You
liable.
don't want to say
Get
it.
that somebody else is a referee. Then no problem.
Okay, so I will let Eric, how about this? I will let Eric to describe, to tell the story. How's that? On that part, on his
Sure.
paper.
As
Okay.
long as I don't have to do it.
Okay, all right, okay. So then I think that's it. Okay, so then.
Okay.
Okay, I will stop. Okay, I will stop sharing, and then okay, so I will stop recording here, and I
Okay.
will share it with Eric. And I think the good news is the latest data from Owen and Abdullah compared with Eric's quote unquote a million sampling, and then laid up right on top of each other. So I have now complete faith in our own students. And Abdullah and then Owen are really amazing. Basically, implemented Eric's code and then reproduce data that right on top of each other. So I have faith in the figure 3, and then so we'll finalize the paper. Okay.
Incidentally, a lot of people have sort of struggled with this one of R squared chain. Has anybody done finalized scaling theory for that?
Mike, people try to do finite size scaling. What did they find was there's a crossing, and everybody thought they made a mistake. And then they referred it to Eric's paper and said, well, that's what Stefan was telling me privately. He was struggling when he was doing his PhD thesis. He thought Eric's paper was the gold standard. What he did must be wrong. So he had to figure out how to get rid of the crossing. Anyway, so the answer is no one has done it properly because of Eric's paper. So Mike, this field has two very important people. One is Mike Kostelis. The other one is Eric Luyten. Both of you made mistakes that screwed up the field, basically, and then give us the chance to write this paper. So I have to thank you for the factor of 2. Basically, that factor of 2 slowed down many people's research because people thought just they're too dumb, and then Professor Kostelis cannot make a mistake.
Sorry about that, because those sorts of mistakes do slip through easily.
Okay. All right. Okay, Mike.
All right.
Okay, so we should sum it up very soon. Okay.
Okay.
Bye-bye.
Great.
Bye.
So when are you going to produce the final version, Sean?
Tomorrow.
Wow.
Okay.
How can you do it by tomorrow?
Oh, well, I have to submit it because Mike, I have a proposal due. I cannot lie. I just went through an NSF training. If you make a factual false statement to NSF, you could go to jail.
Yeah, ICE will come after you, Sean.
Almost everybody who had grants from the NSF in the past should be in jail.
Okay. So we'll have to submit it. Okay.
All right.
Okay.
Bye-bye.
Bye.
See you then.
See you.
Right. Mm.